Keep turn the volume down a little bit on that.
Hi everyone. Thanks for joining us today. Today we have Ashwin Machanavajjhala. He's an associate professor in the CS department of Duke University, and he's a co-founder of Tumult Labs. Ashwin got his PhD from Cornell University. His primary research interest is in algorithms for data preserving analysis with a focus on differential privacy. He received several awards, including ACM Distinguished Member and the ACM Sigmoid Test of Time Award. And today we will talk about negotiating privacy and fitness for use in recent DP deployment in federal statistical agencies. Without further ado, I will invite Ashwin to start his. Thank you.
Thank you, Mariam. Thank you, Adam. Thanks for inviting me here. Is everybody able to hear me well?
Yes.
Okay, great, awesome. I'm Ashwin. Many of you know me. I'm a professor at Duke, and I'm at Tumult right now. So this work is in collaboration with a lot of people at Tumult, including Michael Hay and Jerome McLeod, you may know, and other scientists and engineers there. I'm going to talk about So I'm going to talk about deploying differential privacy, and we've tried to deploy differential privacy in many different situations, and what is emerging is some sort of a methodology for deploying differential privacy. And this is beyond just any sort of code base or software platform that you could use to implement differential privacy. It's sort of a process of engaging stakeholders and trying to understand how we can deploy DP so that these deployments actually work and solve the problems that they care about. So I want to start off with this sort of a flow chart for this methodology, and then go and talk a little bit about specifics. So typically, when you're deploying differential privacy, what we initially start off doing is basically eliciting requirements from stakeholders. So these could be like, what are the statistics that you would like to release? What are the details that you care about in these statistical releases? What may be certain consistency requirements in these tables that you're generating? And also sort of specifying what privacy requirements there might be, what laws maybe need to be satisfied as well. And then based on these, we start by developing some sort of a prototype algorithm, a rough algorithm. And that helps us identify what are the parameters that impact privacy and utility trade-offs, which really is the main thing that is interesting to stakeholders. Like, what privacy am I getting, and how much accuracy can I achieve in the statistical releases that are being made? And then interactively, with stakeholders, we sort of both elicit fitness for use requirements, like how much error can you tolerate in your statistics that you're releasing, and visualize the trade-off between privacy laws and fitness for use, right? And this is an interactive process that we call privacy negotiation. And once this privacy negotiation is done, then we finalize the algorithm, implement it on some platform that is robust and secure, maybe tune the algorithm a little bit, both for accuracy and performance, and then go ahead and release the data, right? And today I'm going to start off by talk about how we instantiate this in one of our projects, which is an ongoing census deployment for the 2020 decennial census. And talk about the problem, the requirements, some algorithmic optimizations we came up with, and how and this sort of privacy negotiation, how the privacy negotiation went for this use case. And then I'll talk a little bit about the platform, the differential privacy platform we're building, on which these releases are actually being made. Talk about the design of this platform, something about the architecture, and some of the challenges we faced designing this platform. For those who might have been in the recent Simon's workshop, a lot of this you might have heard before, but I noticed that there are a lot of others in the audience as well. So hopefully this will be useful for you. I'm not going to talk about, cool algorithms that we created or nice theoretical results we created. That's not the focus of this talk. The talk is to talk about things we did, some lessons that we learned, but most importantly, open questions that are challenging and that we would encourage the researchers to work on. And that's really the takeaway from this talk. Okay, I want the talk to be interactive. So if you have any questions, just feel free to stop me at any time. I don't need to cover everything in the talk. I would rather have a discussion with you guys. All right, so if there are no more questions, any questions at this time? All right, let's move on. So first part of the talk, we're going to describe a specific use case. So in this use case, I'll start with the problem. So this is a disclaimer saying that we were contacted by the Census Bureau to develop some algorithms for the 2020 decennial census. I'm going to describe some algorithms. These are candidate algorithms, like they're not decided to use these algorithms. It's just candidate stuff. Okay, so what is the problem? The problem is the following. So they want to take every individual in the US, and for every individual, they want to release the total count and the sex by age, gender by age, marginal for populations grouped by geography and what they call detailed race and ethnicity. Okay, so detailed race and ethnicity could be something like, could be as broad as, Asian or white, but it could be as detailed as like Bangladeshi, Pakistani, and things like that. So for example, so what the output looks like is a one table per population group. A population group is a combination of a geography, like North Carolina, or Orange County, North Carolina, a county or a state, crossed by this detailed race or ethnicity. So it could be Japanese alone or in combination. And so every individual record has a geo-identifier that maps them to several geographies, in this case 4. And each individual could be part of many races. So these combination of races could map them to up to 18 different races or ethnicities in this vocabulary. And then they contribute a count of 1 to one or many different tables. Okay. All right. So even though we're releasing statistics, we're not doing machine learning, like the problem size is humongous. So the input is pretty large, like you have 350 plus million persons in the US and Puerto Rico, that is large enough. But more importantly, the output size is the one that is really large. So you have, up to 46 counts, sex by age counts. You have over 3,000 geographic entities, and you have over 3,000 race and characteristic iterations. So you're close to 500 million output statistics, and often we're generating 2 terabytes of data. So it's a lot of different output parameters you're estimating from just roughly the similar number of input rows in the data. So what are the fitness for use criteria in this problem? So the stakeholders here care about keeping relative error low. So if statistics are high, statistics are very large, and they can have high absolute error. If they are small, they would like them to have small absolute error. And in particular, if statistics are very high relative error, they would not like that to be published because users may not know how to use them. They care about intermediate breakouts. So beyond like the full sex plus age marginal, they may care about like just the sex marginal, the sex by age, which are the fewer age buckets. And even if these intermediate statistics are not released, they still expect that the users will try to aggregate and derive them. So you should make sure that those errors are not too bad either. The two other important criteria that came in was like, one was the error for the release statistics must be predictable. They would like to know in advance, like, they would like to convey, this is what the error you would expect from these statistics. And they would like that to be predictable and easy to understand. And they wanted the release statistics to be integral and non-negative. And due to the combination of this 3 and 4, like we sort of made sure that there were no other consistency requirements in the data. Like, for example, the counts at the state level should match the counts at the counts at the state level should add up to the counts at the national level, and things like that. We didn't want those consistency requirements because there is both empirical and theoretical evidence that if you sort of add integrality, non-negativity, and these consistency requirements, you often get into bias and unpredictability and error. And so since predictability and error was important, we sort of said, okay, let's not have those consistency requirements, but rather we sort of advised them on teaching the users to deal with inconsistent data and say, provide communication of how to sort of think about the inconsistencies in the data. Okay. So with that problem statement, let me talk through what the algorithm might look like and some optimizations we came up with. And I'm going to discuss the optimizations first, but really these optimizations came out by sort of engaging with the stakeholders in this interactive privacy negotiation we'll talk about later. The simplest algorithm would be to just add geometric or discrete Gaussian noise to each statistic, right? So geometric gives you pure differential privacy. Discrete Gaussian would give you zero concentrated differential privacy, and you would get your integrality for free in both cases. If you compute, the sensitivity is pretty high. Like each record contributes to about like 144 different statistics. And so this sort of naive algorithm would work, but would not have like pretty strong accuracy. So we did some simple optimizations. So first of all, if you look at a geography like nation, you'll have larger counts, right? Larger populations. Whereas, if you look at a detailed race group like Egyptian in a certain county, you may have a much smaller amount of data there. And so clearly the simple thing you could do is like allow the stakeholders to have different, set different privacy budgets for different population groups, right? So that way you can have higher noise for larger groups and smaller noise for smaller groups, right? The second thing that we did was to basically compute only the most detailed statistics and then aggregate. Again, since relative error is the thing that you care about, like as you aggregate, you get more data. And so, this is fine. Because the most important optimization we did was to sort of allow this adaptive choice of statistics. So some population groups are too small to support detailed statistics. Some populations are large enough that you can release a lot of statistics and you still have low error overall. Right? Because the more statistics you release, the more noise you're going to have. And so you don't want the noise to drown out the signal, right? And so we sort of we said, okay, let's set a small fraction of the privacy budget where we measure how much population is there in these groups. And if the population is large, then we release a detailed set of statistics. If the population is small, we release a small number of statistics, right? And so, for example, here, if your population group was European and Californian with a size of 20,000, you get a noisy size of 19,000, then it will get a sex cross age with 4 buckets rather than sex cross age with 9 or 23 buckets. Okay. And this whole thing was built on Tumult Analytics. We'll talk more about this, its interface later. But let me talk more about how did we even come up with these optimizations, and how did stakeholders think about privacy, fitness for use, and how did they set these parameters, right? So typically, this is what a negotiation looks like. So there is a data curator, in this case, the people inside the Census Bureau who cared about the privacy of the data that they were releasing. And there's an analyst. In this case, the analysts who are partly people in the Census Bureau who cared about the accuracy or the fitness for use of the data, and the stakeholders outside of the Census Bureau that they interacted with and got requirements from for why these data were being used, right? And so in this case, example negotiation would be like the curator says, oh, we came up with this, basic algorithm, and at this at a privacy loss budget that we like, you'll be seeing a margin of error of about 25 in that comes. Okay, and the analyst may come back and said, well, 25 is a lot of error. For the national level, maybe it's fine, but at the county level or smaller levels, it's a lot of error. So can we increase the privacy loss? And the data curator may come back and say no. Well, if that's all the answer is, then that's not a negotiation. It stops, right? So we don't want a negotiation to stop at this point, but rather we want to give them tools where they can say something more creative, right? So for example, you want to say, hey, you know what? We can't increase the privacy laws, but we can do this other thing where we devote more of the privacy laws budget to like county estimates and less to national level. So maybe the national level counts now have a margin of error of 50, whereas the county level estimates are margin of error of 11, right? And the analyst is like, oh, that sounds much better. And then they can continue with other requests that they have, right? And so we've seen this play out in many, many scenarios, definitely in this scenario that we've had here. But essentially the thing is like, you need to provide a language for the analyst to sort of try to get what they want, right? And often like they don't know what is possible, and this pricing negotiation could help them see what the possibilities are, and then try to get the best they can for a certain privacy loss, right? And in fact, the algorithmic optimizations that I talked about before were all motivated by this privacy negotiation. We started off with the simple algorithm, and then they asked this question, and they said, oh, maybe if we split out the privacy budget, then that'll help them. Oh, if we do this adaptivity, it'll help them even more, and so on. Okay. And but it's not, you also need tools, right? Like you also need to be able to see quickly what the impact of privacy loss parameters are on errors. So what we built was like an Excel spreadsheet tool that listed what are all the privacy parameters that impact accuracy are, and then showed it to these stakeholders, right? So what does this tool look like? So it's basically, you could specify the margin of error that you require at different population groups, right? And then you could visualize what the privacy loss would be for those accuracy estimates, right? It'll also show you the total privacy loss. And then it'll also show you at the level of the tabulation for each of your statistics, what the margin of error is. And now this is basically powerful because now, stakeholders can go in, the curator can go in and say, hey, this privacy budget is too high, so I need to reduce it. Or the stakeholders may say, oh, you know what, I can reapportion these margins of errors in these ways. Maybe I don't care about the county levels. I will eliminate that from my computation. I will add place because place is more important for my use cases. I can tweak the margins of error and then see what the overall impact is of this algorithm on the margins of error in all of these statistics, right? And so this basically gets the differential privacy experts out of the loop, right? And lets the data curators and the analysts who are subject matter experts think about how to make these trade-offs, right? And we are there to sort of there to advise them on how to sort of think through what a privacy loss is and think through why the margin of error grows in a certain way and so on. Okay. And so just sort of, we've done this sort of analysis for this data product, and at the end, like these were some examples of MOA targets that they came up with for different population groups. And based on that, for our algorithm, we can sort of figure out what the total privacy loss is. So under the geometric mechanism, we got a privacy loss that was sort of like 15 or so for PODP, but for the discrete Gaussian, we got a privacy loss of 12. And these are not like finalized numbers or anything, but these are like sort of sample ways to see how these what the interaction is between the margin of error and the fitness for use constraints and the total privacy loss. Okay.
Ash, on a question. So the numbers we're seeing here, these are the epsilons corresponding to, oh, maybe you're going to see exactly that.
Yeah, exactly. So these are the epsilons corresponding to the ZCDP. The ZCDP value itself was less than 2. You can add up the numbers in the last total column to get the ZCDP total. But these were approximate DP equivalents with delta of 10 to the minus 10. Is that your question, Adam?
Yeah, that was my question. Thanks.
Yeah. Okay. All right. So to summarize the first part of the talk, the problem here was to sort of use, provable privacy to release these total counts and sex plus age marginals. There were hundreds of millions of inputs and close to 500 million output statistics. The important thing was usability of the output statistics. That was extremely important to them. So even if these are noisy statistics, they had to have a way in which they could explain it to users and make them comfortable using. So they wanted the error to be predictable, and they knew that users will try to derive one statistic from others. Non-negativity and consistency is hard with predictable error, and that was one of the first negotiations we did. Was like they wanted everything. They wanted integrality, non-negativity, some sort of consistency, and we told them, like, if you add all of them, you're not going to get predictable error. And so that was the first step of the negotiation. And I think this privacy negotiation is something that keeps coming up every time we do a real deployment. We have to have tools that allow stakeholder-informed algorithm design and setting of parameters before the algorithm is deployed, so that the feedback from the stakeholders is gotten before you release data and not after, and that is very, very important. I want to say a few more words about this privacy negotiation. We think like it's an area ripe for a lot of interesting research, and this, I would argue that this privacy negotiation is almost an unavoidable step whenever you're deploying private data release, at least for high stakes problems, right? When people really care about the privacy of the data and people really care about the use of the output statistic. And this is true definitely in federal statistical agencies, but it's also true in a lot of different settings, in healthcare settings where the data is being used for research and so on, right? And often almost always what we see is like the analysts want the moon. Like they want everything from the data. They want the data to look exactly the same as the original data, right? But then the fundamental law of information reconstruction disallows giving away the moon, right? If you want, forget about differential privacy. No matter what you do, you cannot give away the moon, right? And so what we need to do is have a way in which you can convey this information and allow them to sort of negotiate what access they can get, right? And the problem is often very underspecified. Like analysts often know what they want, but they can't verbalize it, right? The perspectives on error and utility can vary a lot. Like in this use case that I mentioned, the fitness for use requirements are like margins of error and absolute error. So it's fairly easy to understand. But there are other use cases where the error metrics are very different from what we usually think about. Like in one use case we saw, what they cared about was ranking of different statistics. So releasing one statistic for each university. And then they would say, oh, in the real data, people might say, how does Duke University and Harvard rank according to this metric? And with the noisy statistic, you would like to make sure that that same order is preserved. Of course, if you preserve the order with probability 1, you can reconstruct the underlying data, right? And so sort of you need to have like new kinds of metrics to think through what these utility metrics are and how you would optimize for them. And data owners want privacy, but these privacy parameters and the privacy definitions often are not like, they're not set in stone, right? Like for example, we started out with pure differential privacy in this project. And then they said, well, we don't really care whether it's pure differential privacy or approximate differential privacy or zero considered differential privacy. As long as you can give a decent explanation for what the privacy guarantee is, you can use whatever you want, right? And in fact, we switched from pure to ZCDP because we could give Gaussian noise, and that had better properties than Laplace noise. So really, again, like, yeah, this is underspecified. So this sort of
Ashwin,
yeah,
can I ask a question? So how did you thread the needle between this? You mentioned this conflict between predictable error and sort of formatting and consistency requirements, like non-negativity and integral response and consistent tables. So how, in the end, how did that play out?
Yeah, I mean, that's a very good question. I think we were able to what we described was things that could happen if you try to enforce the non-negativity and consistency, right? Mm-hmm. How you can predict what the error could be, how like you can have certain sort of sparse, in certain sparse areas, populations could be under or over reported. So we could give examples of those and the kinds of bias that could be introduced. And I think people are very worried about bias. Like in general, across all use cases, people worry that bias is a bigger problem than sort of variance error, because it's harder to predict and harder to estimate. And so I think that sort of played into them saying, okay, let's work without consistency. But even the stakeholders were thinking through like, oh, you know what? Maybe it's okay if there's no consistency. We can explain to them that this is the way they should think about it. Like if you're thinking about a national count, don't look at the state count. Just directly go look at the national counts, and then that would be the best way to estimate what you're doing rather than adding up the states. and things like that. So they are already sort of thinking through how they can communicate the lack of consistency with their users. Right?
I was going to just ask a related question. So I guess the integrality you get for free using the geometric or discrete Gaussian, and then is the non-negativity kind of for free by the fact that you are only doing the counts that are not too small?
Yeah, to some extent, yes. So we are already like sort of thresholding and saying, hey, if the counts are smaller than something, then you'll only release a total or something. We're still sort of talking with them as to even eliminating the non-negativity and sort of replacing that with like a post-processing step where they suppress small counts. That might actually be simpler because they do want to sort of, I think, show like the sex marginal by adding up sex cross age counts, in which case you don't want to do non-negativity and then do the post-processing. You want to like first add them up and then suppress things later. So we're talking about that, and yeah, they think that might be a good way to go.
Thanks.
Jörg?
Yeah, Ashwin, I also have a quick question regarding the privacy negotiation, because I think that's the, I understand that this is a key part of all this. But, in your picture, you have this curator and then you have the analyst. And so I see, it's pretty easy if you have one stakeholder on both sides in some way. But if you think about the census situation, obviously they have so many users of the data and they have a lot of them that they are not even aware of. So can you say a little bit how they try to, understand what the analysts prefer in terms of what level of accuracy on which geographical detail?
That's a very good point. Yeah, thank you for bringing that up. So yeah, in this census use case, at least, in this use case, there was one division in the census which was responsible for the statistics being released. There are other use cases where multiple divisions were involved. and so in that case, we had them elect someone as a representative, but have discussions happen to both those divisions. But in particular, what this division did was like they went to their users, got user stories of what are the statistics that they care about, created a long list of use cases and used those use cases when working with our tools to think through what should the margin of error should be, what statistical, what geographical levels they care about, what detail races they care about, and so on. So they used the use cases in hand, and then they did it. Now, once they have a sense for, okay, this is what might work, they're going back to their users and running workshops to show, hey, this is what we are doing. What do you think? In fact, this week there is this big demographers conference called, I'm going to make a mistake in the name. It's called Population Association. I'm sorry, I forget the name, but basically there's a biggest conference in for this. One of the groups that did this negotiation for one of the data products is going and using our tools and showing them, well, this is the tool we use. This is how we came up with these requirements. You guys do the same and tell us what feedback you have. And so they are trying to engage stakeholders outside the census as well in this process. Yeah.
So I have a question.
Sure.
So I wonder this privacy negotiation is happening before we answer all queries, right? So what I was trying to understand is if we select the privacy budget adaptively, then how will we account for the total privacy loss? But if this privacy negotiation happening before we answer all the queries, it wouldn't be a concern.
Yeah, that's an amazing question. That's a great question. In this project, we got lucky that we could do the privacy negotiation completely with analytical estimates of error and with old data. So basically, all of this negotiation, everything in this tool that I showed you, everything that I showed you in this tool was analytical formulas, and anytime we use data, it was old data. And so this was sufficient to do all of the negotiation. So none of the real data was ever touched when doing this negotiation. There was another use case where we could not use analytical error estimates, and this is one open question for you guys, which is because they needed medians and quantiles, and we did not have, we tried to use analytical estimates, but they were very, very bad. And so we had to use the data. But luckily for that use case, we could generate synthetic data, which after the fact we heard was like the negotiation that you would have done on the synthetic data would look very similar to the negotiation you could have done on the real data, because the synthetic data was sufficiently good for representing errors. But there will be cases where this has to be done on the real data. And so that was one of the open questions that I was going to raise, like, how do you think about this privacy negotiation if it is done on the real data and account for the overall privacy loss? Good question, thank you.
I see, thank you.
Okay, if there are no further questions. So yes, I think this is an important problem. I think there is a lot of right research for building technical tools to help this process. So I think the first thing is like explaining errors is important, but explaining errors privately is also important. And so how can you develop mechanisms of permit releasing both the answer and uncertainty estimates for these answers? I think this is an important problem. I think there's some initial work going on, especially definitely with confidence intervals for basic statistics, but I think more work is needed here. As we heard from one run, so we need to make this privacy negotiation privacy preserving, right? Simple mechanisms can permit privacy negotiation using analytical error estimates, but it's more sophisticated, more challenging as both the kind of statistics become more complex, but also the sophistication of the differential privacy algorithms increase, right? Like if you're not doing a simple Laplace mechanism, but rather you're like, taking your data and then doing some sort of clustering and then releasing counts for each of these clusters, then you need to estimate the bias and the variance. And then now you need more sophisticated ways to release error, right? And I think more generally, like at a higher level, we need tools to help data owners and data analysts contextualize privacy loss parameters and verbalize their accuracy requirements. And this is a little more open-ended. I know that there are people like Priyanka in the audience who are working on visualizing, privacy utility trade-offs and doing some cool stuff there. I think we need more work here. Like, how do we get users talk about privacy and accuracy in a way that can help us, streamline this process? I think this is going to be the long pole in the tent when we are going to deploy differential privacy and have privacy mechanisms in general, not just differential privacy, adopted with strong guarantees. Okay. With that, I'd like to move on to the next part of the talk, but before that, any questions? Yes, Kobe.
Yeah, so Ashwin, can I ask what magnitude of epsilon you were achieving in this project, and whether you think that explaining, so maybe first you will answer this question.
Yeah, so in this, for the margins of errors that they thought could be a potential target for this use case, like the, under rho ZCDP, the rho was, I think, 1.5, which translated to an approximate DP guarantee of 12 and with delta of 10 to the minus 10.
Okay, great. So I think that most explanations of differential privacy refer to the small epsilon regime. And here you're talking about large epsilon. Maybe you could speak a little about how different is it to explain and negotiate privacy at the higher levels of epsilon from the traditional explanations which focus on small epsilon?
Yeah, I think that's a good question. We don't have a very good answer of how we are explaining an epsilon of 12 is good. We know how to say epsilon of 100 is bad, or a row of 10 or 20 is bad. We know how to say an epsilon of 1 or a row of 0.1 is good. In this middle regime, we don't know how to say it. And we are not, frankly, we are not saying anything at that point. We are rather saying, you know what, I mean, we are actually using some of the guidance that OpenDP is giving, which is like, 1 to 5 is strong privacy, and 5 to 20, is robust privacy. But beyond that is bad. But we are not saying anything about in terms of what you're talking about. And this is something where we would like some advice and guidance.
Ashwin, when did OpenDP say that?
We saw it somewhere in some OpenDP stuff or Harvard stuff, or some sort of guideline like this. And so, I mean, this is an example that I saw before. That's why I mentioned it. If you didn't want to stand by it, then please let us know. You know what?
Yeah. I'd like to track that down. If that was just in some like prototype tool, I mean, just want to be careful about what we're.
Yeah, we don't use that. I've never used that. We've never used that with the client. But I think it's these are challenging use cases. There's a lot of data that is very important, and in the end, like I truly believe that this is like a social choice problem, right? Like if the data is very, very useful, right, and we have to release them, and the goal is to have these privacy laws as small as possible, and yeah, we'll see where things end up.
I have one more quick question. Did you look at sort of, given that you're looking at Gaussian noise, sort of a gradual release approach where you kind of add a little bit, a lot of noise and then refine, save some of the privacy budget to refine certain queries, possibly adaptively based on the magnitudes of the.
Yeah, we are looking. Yeah, we are looking into those algorithms. I mean, one thing that will become clear from the next part of the talk is we're also trying to build this into a framework, right? And so now you're starting to talk about really complex privacy analyses that have to be supported, but automatically reasoned about by a system. And so we've thought about those algorithms. We have not implemented in our platform yet. And in this specific use case, I don't think they buy a lot, but those are things that we are looking into. Yeah.
Yeah, I guess for Gaussian noise, the accounting is pretty easy, right? The doing things gradually is pretty simple.
Oh no, the accounting is easy. That's right. Mm-hmm. Yeah.
But yeah, for some of the other mechanisms, it's a bit more complicated.
Right. I mean, there are maybe I'll come back to this in the end. Right.
Great.
All right. Sounds good. So now that's a natural segue into, let me talk a little bit about the platform we're building, because everything that we implemented, all the differential privacy algorithms implemented are built on this sort of extensible platform for differential privacy. And the reason we built yet another platform for differential privacy rather than using some of the open source library available was that none of the open source libraries that are out there actually met our needs. So some libraries offered scalability, but they baked in a particular privacy calculus, which is not going to be scalable in the sense that different use cases may need different ways of accounting for privacy, right? Like you may want pure DP in one case, in another case you may want like more adaptive composition and ZCDP. In other case you may want like individualized privacy accounting, and so you don't want to bake in any one privacy calculus, right? You want a framework to be extensible so you can add in other privacy calculus after a point. In fact, like we started with pure differential privacy and we wanted to move to ZCDP. It was just adding a few more operators, and everything just sort of went. There are other libraries that are very extensible, right? But are not designed to scale. And so their interfaces are sort of harder to use for naive users. And so because of these we decided to build our own platform. So I'll talk a little bit about the design requirements, give you a feel for the interface, talk about the architecture, and more importantly, talk about some of the challenges that we are faced while building this. Okay. So to design this, so our platform is currently being used by several clients, notably at the US Census Bureau, IRS, and even the Wikimedia Foundation. And it soon will be open source. So we'll let you know once we are sort of open source. If you want to try it out, please let us know. We can show it to you or give you early access to it. So it has multiple parts. It has a easy to use API for analytics. So it has SQL types, transformations like filters and joins, and to compute, differentially private aggregations like counts and sums and quantiles and so on. It supports multiple variants of differential privacy, but it's built on top of an extensible framework that integrates with Apache Spark, and so it can scale to really large inputs and outputs. So let me tell you what motivated us. What are the design requirements that motivated our system? So the main thing was usability. So we want to make interfaces that are simple and intuitive for new users, and develop training materials that help users to get up to speed. And it's not obvious how to do this because people have been working with data for a long time, and there are like well-established, data analysis pipelines like Pandas and Spark. But when you go to differential privacy, there are certain things that you absolutely have to do differently, right? Like you have to sort of specify that there is a sensitive data set. You have to limit the number of accesses you make to the data set. You absolutely have to change certain things. And the goal here is to like change as little as possible, and then force changes only when they're absolutely necessary. And this is a very, very hard fine line to traverse between sort of usability and the ability to actually get differential privacy or private functionality, right? So to give you a quick example of what our interface looks like, you start by defining a session. The session basically encapsulates a structured data frame, and specifies like a private, and then you specify a privacy guarantee for the session. So in this private session, you can do whatever you want with the data frame, and at the end, you will guarantee a pure differential privacy guarantee with epsilon of 1.7. If you wanted to change it to row ZCP, you would just say privacy budget is row ZCDP of 0.1, and it will just take care of the accounting underneath. And then you start writing queries on your data. So a query is like a Spark-like thing or a Pandas-like thing, where you start with the data and say, hey, I want to filter all the rows with age less than 42, I want to group by zip code and get a median income. And already you can start seeing there are some changes here, right? Like when you specify a median, you need to specify a low and a high, right? We could infer these underneath, but again, there is like this fine line between how much you can do under the covers and how much control you want to give the users, because often users want that control as well, right? And these are things that we're still working on and fine-tuning. And once you specify a query, then you can say, evaluate this query with a pure DP budget of 0.8. And this will basically allow you to get the noisy results. And the noisy results are, again, a Spark data frame that you can go and work with and do whatever you want. Okay? Because our platform is literally used for production, it must also be expressive and scalable. Right? So in terms of scalability, you want to scale not only to large inputs, but you also want to scale to large outputs. And often the large outputs is the killer, because like you have to generate these outputs, you have to generate so many noise variables, and you have to like be able to handle them. So that's the harder part of it. And so we do that by integrating with Spark, and I'll talk about Spark later because that brings its own host of challenges. And in terms of expressivity, we have real use cases. They have complex requirements and often requires advanced features. And so here's some small collection of sort of advanced features that we needed to implement even for our initial engagements with our clients. And in particular, I'll focus on these include things like adaptivity, joins, parallel composition or concurrent composition under ZCDP, which is still sort of a fully not a fully resolved problem even in academia, and so on. And so I'll illustrate one of these, the adaptive selection of statistics, since we talked about it in the census use case as well. So this is going to be a little code walkthrough, a little more complicated than the previous example, but just bear with me. So in this case, as I said, we're going to spend some of our budget to get a to divide population groups into big groups and small groups, and then depending on that, release different statistics for each. So we're going to create a privacy budget. And then first, you're going to get an overall histogram of these different groups, of the total population of these different groups. And then we're going to say, oh, which of these groups are large groups and which of these are small groups. Okay. Now we can take these labels and join them back to our original data using a join operator to sort of associate each sensitive population group with either it's a big group or a small group. And now we can take our session and partition into multiple sessions. Now, and each of these sessions, basically each of the session takes a subset of the data. In this case, one subsession gets the small groups, the other subsession gets the big groups. And now that you've divided the data, we can run different differentially private algorithms on them. And they both get this remaining privacy bucket. Because you're divided, you can actually do parallel composition, right? And now we run one algorithm on one group, which is just getting the total count with the remaining privacy budget. And on the other group, we do a little more complicated thing where we're getting a group by, or not just the total, but the age buckets as well. So our algorithm, the real algorithm in the sense is a little more complicated. We don't have 2 groups, you have 4 groups, you have many different thresholds that we split things on. There's more business logic going on and so on. But you can sort of get a sense for the kinds of advanced features that we have to support and the kinds of advanced things you have to do in terms of privacy reasoning, because now we need to think about, branching your privacy proof into 2 parts and allowing for adaptively choosing a different privacy mechanism on each side. And so these come with like some challenging sort of questions in terms of automatically generating proof of privacy. Okay. So of course, as we're building this, we're getting new feature requests, right? And so we need our system to be extensible, right? We want to incorporate advances to DP, new mechanisms, new privacy accounting methods. And this requirement greatly influences the architecture that we use. And finally, we want correctness. So we want to be able to generate proofs that the computation is differentially private. And also we want to avoid unintended privacy leaks. I mean, clearly we all have heard a lot about floating point and how floating point could create side channels. Turns out like using an external compute engine like Spark also creates side channels. I'll talk a little more about that in a few slides. Okay. So in terms of architecture, we have this multi-tiered architecture. So the top is this sort of easy to use interface where you can specify queries and evaluate it. But then when you specify queries at the top level, what it does is it compiles these queries into plans, into differentially private algorithms that are the plans that are then executed on this extensible framework we call Tumult Core. And so what is this lower level? It's inspired by the OpenDP and Ectelo kind of system designs. But basically, it's a bunch of operators. These operators can be divided into 3 kinds. There are like transformations and measurements. Transformations take data and transform it into another kind of data. And measurements take data and generate results. And these are sort of differently private mechanisms. And importantly, the privacy properties of each of these are associated with these measurements. So you always get a privacy promise when you use them. And now you can derive new components using these combinators. Like, for example, you can have a chaining combinator that chains 2 transformations. You can have a composition that basically applies multiple differentially private mechanisms. And this could be either batch or it could be adaptive and many others. And so these properties are derived from the properties of the combined operators. And so I think this is where sort of really challenging algorithms. This is where we need to sort of think through how to incorporate complex algorithms so that you can automatically derive their privacy properties from smaller building blocks. Okay, and so complex DP computations can be built from simple components. So for example, if we have a group by average, it uses like several base transformations, several base measurements, and several combinations. And it's, as I said, the privacy properties are derived automatically, and composition helps you, composability helps you extend it to other frameworks. So for example, we started with pure DP, and to get GCDP, we just add a few different measurements and chain combinators. And this is very related to the OpenDP framework, but the implementation is very different, partly in terms of the design choices we made in the kinds of combinators and transformations we implemented, and the kinds of privacy analysis we do, and also because it sort of uses an external compute engine like Spark. Okay. So I want to highlight a couple of challenges when we're building these, and these are sort of more sort of high-level challenges. There are some, of course, some nitty-gritty open questions that we keep coming with all the time, but these are sort of larger themes. So I wanted to mention these larger themes before I conclude. So one is this integration with an external compute engine. So what is Spark? Brief, quick refresher. So Spark is an abstraction that basically aligns nicely with this sort of functional paradigm of the privacy framework. So it has objects. These are like data frames that represent collections of unstructured data. But these are not real data frames. In fact, they are sort of just a representation. They're actually different. The rows are split across many machines, and this is just a single sort of handle for that data, right? And then it allows you to specify to do functions. So you can do filters, you can do things like maps that allow you to, like, for example, take a noise mechanism and push it to different machines and so on. And so when you evaluate all of these functions, you get another Spark data frame, which is again another representation of data that is stored across many different machines, right? And largely, like, the abstraction works very nicely with what we want, right? Except when the implementation, at the implementation level, it actually sort of introduces some interesting vulnerabilities. So to illustrate the vulnerability, let's take this example, right? So let's say you have a data frame, you are doing some group by noisy count after grouping on some set of attributes, and you get some, output data frame with noisy count. So let's say you start with, something like census data with sex and location, and then you get an output for every gender and every state. You get a noisy count, right? So in principle, this is all great, but then here are a few example vulnerabilities that we found. Two of these we've actually solved. One of them we're still working on. So the main question really is, like, you have a Spark data frame that results from DP computation. Is this immune from post-processing or not? Because you want any result from DP computation to be immune from post-processing, right? So here is one way in which it is not immune from post-processing. So if you generate this noisy counts, and then you can use this function called show. It just shows you what the data frame is, right? And show, basically, you need to say show because this data is distributed across everywhere. So if you want to even see the rows, you have to collect them in one place and show it to the user, right? It turns out that Spark is lazy. So it doesn't do anything. When you say, noisy counts equal to group by and add noise and do all of this, all you get is a handle on a plan. This is a plan for computation. And when you do something like show or print or save, that's exactly when it is actually evaluated. So the first time when you say show, it says, oh, okay, I need to evaluate this plan. It evaluates it. The next time when you say show, again, it tries to evaluate it, but now it evaluates it a second time. And since it's not a deterministic piece of computation, right? You add randomness a second time, right? And that is a vulnerability because you don't want them to keep showing it over and over again and add noise over and over again. And this is something you absolutely have to handle in a system like this, right? This is something that we were able to solve fairly easily. Another thing is, like, the abstraction here is an unordered collection of rows, right? But in practice, like, any implementation has to order the rows somehow, right? And so it turns out in Spark, like, the ordering is based on whether the count is 0 or non-zero, right? And so just based on ordering, you can tell, hey, you know what? The things in the bottom are zeros, the things in the top are non-zeros. And so that leaks information. And note that these, I use the word sort of vulnerabilities and not side channels here, because before people have talked about side channels where, like, you can use other information like timing or things like that to infer things about the database. Here, this is in the output. It's a property that's in the output. It's not a side channel. It's a channel. It's there, right? And the output itself is causing these sort of vulnerabilities to be present, right? And so this is again something that it's fairly easy to fix, and we fixed it. third one is a little more complicated. And essentially what happens in a complex system like Spark, but it's true for any database system, is that you have what is called a logical plan and you have what is called a physical plan. A logical plan logically tells you these are the operations that need to be done. But to implement it, you may choose to do it in different ways depending on how the data is. For example, in Spark automatically chooses how much parallelism there should be based on the data, right? And so we were able to create examples where if you add or remove one row in the data set, it uses different plans to compute the data, and it generates different number of parallel things. So how that manifests is like how many files are written out. Like when you write to CSV, since these files are very large, you don't write a single CSV. They read one CSV per partition of the data. And so if the number of partitions is different depending on you're adding one or more rows, then you can see based on the number of partitions which word you are in, right? And so again, like these are kinds of things. This is something you're working on, but these are the kinds of sort of new vulnerabilities that come in if you use an external compute engine. And these are, as I said, these are a very new kind of side channel attacks. And I wouldn't even like to call them side channels. It's not a side channel, it's a channel in the output itself. And often these are highly non-trivial to handle, right? I mean, the reason why these database systems and Spark do optimizations inside them is because if they didn't do those optimizations, nobody would use them. They would be very slow, right? But these optimizations are the very ones that are data dependent and could introduce, these sort of vulnerabilities. You could use oblivious data structures, but there are known negative results that show that if you use oblivious data structures, certain operations like joins will be extremely slow, right? And so this is like a question, open question in oblivious data structures anyway. And it's like, but more generally, like we could go vulnerability by vulnerability, but more importantly, how do you model these external compute resources? How do you sort of have a systematic way to capture, like, this is the model I'm in, and like these are all the kinds of vulnerabilities you can capture in this model. And so we would like to have that kind of a deeper understanding or a deeper modeling, so we can say, oh, this is a guarantee we can give. Under anything covered in this model is handled. Anything outside that model, we don't, right? And that's we're still sort of grappling with that a little bit. And it's also a fine line, because you also want to give users control on how to tune for performance. Because if anyone has used Spark before, if the first Spark program you write will be bad, will be very slow. You need to tune it so that it actually works well on your data. And so these are some of the challenges we are seeing with using external data engines. Okay, another big theme that has arisen is explainability and transparency. And there's explainability and transparency requirements from two scenarios. So one clearly is from the data user or the data scientist, right? Like they really want to know what do you do with my data, right? Like you don't want them to take your answers and make wrong conclusions and write papers about things that are purely wrong, right? You want them to understand this is how the data was clipped, truncated, noise added, so that they can understand what the answers of the data are. And this can be fairly unintuitive, right? There's some nice work coming up about confidence intervals and so on, but there's a lot more that needs to be done because differential pricing algorithms are very complex from a user's perspective, right? But the other perspective is from a privacy officer's perspective. Like they want to know, why is this data safe to release? And you also want to have some explanation saying, hey, this is why the data is safe to release. This is how the data was perturbed. This is how the data was clipped. This is how each individual in the data's privacy guarantee degrades, and also to facilitate third-party audits. And again, like there's a tension between like this explanation and transparency versus like the wanting to hide details from the user so they can adopt it. So I think that's a fine line that you have to show. So to conclude, I mean, we talked about two things. We talked about this methodology for deploying differential privacy, where you want to, bring stakeholders in the loop before you do anything rather than after, and then iteratively work with them and do this privacy negotiation so that you can have successful DP deployment. We also talked about, some of the how we architected a DP platform, some of the design decisions that influenced it, and some of the challenges we are sort of open questions that are arising as we build this platform. With that, thank you very much. If you're looking for jobs, we are hiring, especially for scientists. So please ping me. And if you want to try out our platform, just go to this website and we'll be happy to give you a pre-release that you can work with. Thank you very much.
Any questions?
I have another question. Ashwin, you mentioned transparency in the context of sort of data analysts and privacy officers. This is a little outside the problem you're trying to solve, but what about explaining to people why this type of approach might be useful at all? Like why it's a good idea to add differential privacy, why you can't just suppress small counts or something. I realize that mostly you're operating with people who have either kind of been convinced that it's a good idea to use differential privacy or been told, been forced to it. But have you, in terms of reaching a broader set of applications, it seems like that's also an important component. Is it something you've encountered, or do you have any lessons on how to approach that?
Yeah, definitely. I think that's a very good question. Like this last slide that I had was more tied to something like to the platform. And I mean, if you're using the platform, you're already sold on differential privacy. So this is this kind of material that helps people get convinced that you need differential privacy is a little more upstream. And I think that's it's very important to be able to say that why you need differential privacy. Some of the things that have convinced people to move to differential privacy, other than you have to do it, have been one, privacy officers or disclosure review boards or whoever is in charge of giving access to a certain data set are finding it extremely hard to use legacy techniques and justify what they're doing is safe, because the volume of the data requests and the granularity of the data requests has been increasing year after year. And at least in some cases, the reason they're moving to differential privacy is basically that you can automate these choices, and we need to think about things like privacy budgets, which are quantifiable. And so that's a big draw for people, right? So that gets people over the hump when you say differential privacy. Of course, the next question is like, is this going to be accurate? Is this going to be useful, right? That's the next question that comes up. And at that point of time, like talking them through either, success stories, or even like saying, okay, let's take your problem and see what the trade-offs look like, right? And showing them the trade-offs, again, helps them a lot, right? Actually seeing, oh, I see, this is what the trade-off is. So it's not like what I've heard that you can't do anything with differential privacy. Like you can do something with differential privacy, but then there are some limits, and I have some control on what I can do with those limits. I think that helps people also a lot. I think talking about definitely the census reconstruction attack has helped a lot of people say that, hey, this is a big problem. This is a vulnerability that another statistical agency has seen. So we should really pay attention to this. That helps. A lot of people, even in non-government settings, have never heard of these reconstruction attacks. They've never, and if you tell them this is what the census is, they're like, really? You can actually do this? Okay, now we need to pay attention to what you're saying. So I think telling stories like that helps a lot as well. So I think creating material that can talk to these points is something that will be amazing. Like, and you guys write amazing blog posts. You have a lot of presence, and you have name recognition. Like if you can create these materials right? That would be very helpful.
So what about specifically the problem of getting people kind of over the bump of wanting to like share the data? You know, like the sort of like, I'm sure you've had this conversation with people in many forums where they're like, okay, well, you know, what are you going to do to the data so that I can then publish like the data or share, you know, send over the, you know, the data set? Like, do you have any, any words of wisdom along that, on that front?
I think there are both mandates and desire to share data. I think there is plenty of that. Like from all the discussions you've seen, people want to share data. Ideally, they want to share synthetic data, like data that looks exactly like this, but somehow magically privacy preserved, right? But of course, synthetic data is just a panacea, right? Like you don't even know what synthetic data preserves. But there's a lot of appetite for sharing data. It's mind-boggling how many people want to do this. I don't think you need to convince people that they should share data. It's like more about like, you know, convincing them to use like safe techniques to share it.
I guess, no, I didn't mean like convincing people to share the data, but convincing, like in the conversations I've had with many, you know, groups, it's sort of the move from like, getting even to the point where the conversation is about, okay, what are the statistical features in this data that you want to preserve, and how accurate do they have to be? Like that, just getting to that conversation seems like an enormous jump in many settings, right? As opposed to, well, I just want to, you know, I just want to release the data that's useful for like everything.
Yeah, I mean, yeah, maybe I should be talking to people you're talking to. But in my experience, like, yeah, I think there are people who just want to share the data, but then I think there's a lot of fear about, you know, regulation, crackdown, the GDPR, CCPA. Like there's a lot of pressure on people to not do things the wrong way, at least in the last, you know, couple of years. And people are very worried. That's the feeling that I'm getting. So people are not just sharing the data as is, or just doing some basic stuff.
Right. No, but it sounds like the people you're dealing with have already gotten to that point where they're like willing to even have a conversation about like making a relatively explicit list of things that they want preserved about.
Right.
Okay. Thanks.
So there is one question in the chat by Dimitri Prokorenko. I hope I pronounced it that right. Maybe a side question. How do you handle the USA EU compliance, CCPA and GDPR? Any tips or options to measure such compliances except consulting with the legal department?
Yeah, that's a very good question. We get this question a lot, and we wish people like Kobe gave us the answer. So, like one of the top questions we get is like, is this HIPAA compliant? Is this GDPR compliant? Is differential pricing CCPA compliant or GDPR compliant? Like basically, but then we have to talk to them and say, I mean, really, that's not even a question that's not even a well-formed question, because GDPR is more about how the data is processed, where the data is processed, who is processing it, and some limits on that. And this is more about like statistical disclosure. We do talk about some of the results that Kobe and the students have had, like how, you know, singling out is like differential pricing guarantee is much stronger than singling out, and that's something that has been that's a requirement of GDPR, and this is even stronger than that. And another way we've had success talking to people was like, when people talk about HIPAA, right? In HIPAA, there are two ways you can guarantee, ensure that what you're doing is safe. One is by just redacting a bunch of variables, which renders the data often useless. And the other way is to basically say, you know, we don't redact those variables, but we go consult with this with this expert, and there are like 5 or 6 experts